All right, so we've set up our problem for example 4.5. Now we need to write our mass balances and solve. So the trick with this problem is less all of the worrying about density and molecular weight and things like that, and more worrying about what are you doing a balance on. So remember, our strategy here was to take a look at the total overall system first to solve for M3. So that's what we're going to do first. So the overall balance, we're going to have input equals output in the system. So what we want to do is we want to look at the boundaries of our system and we see what's going into our system. So let's flip back over to our diagram. What goes into the overall system boundary? Well, the things that go in are here, this 100, and here, this 30. So if we flip back over, the input has 100 and 30. Now let's go look at what leaves. Well, the things that are leaving this outside boundary are 40 and 30 and M3. So if we flip back over, you'll see that the output here is the 40, the 30, sorry, that's sideways, and the M3. If we solve this out, you'll find that M3 is equal to 60 kilograms per hour. So there's one of our variables. So if we go back to our process flow of how we're going to do this strategy, the next thing we wanted to do is we wanted to balance on unit 1. As an aside here, we could do a balance on species A to find what the fraction of A in 3 is. So this basically is saying that the sum of the masses of A in is equal to the sum of the masses out, right? This is input equals output of the total system. So we would take the mass fraction in each stream of the inputs and the mass fractions of each stream of the output, multiply by the mass fraction and the new M3 that we just found, and we could find the mass fraction of A. So that's going to give you the composition, and then 1 minus this will be the composition of X3A in the system. So that's just as kind of an aside that's how you would find the composition. The next step is to do our balance on unit 1. So unit 1 has, let's flip over, this 100 coming in, this 40 leaving, and this M1 leaving. So what that means is that the overall balance is 100 in equals 40 plus M1 out. So this is output. So that gives us an M1 of 60. If we do the same thing that we did above, this is taking mass fraction times mass flow rate. Let me move this up a little. There we go. This is taking mass fraction times mass flow rate all the way through to find the mass fraction of 1A. So same process here. I'm kind of skipping over this because we've done this a lot in other problems. You can pause this video if this is confusing. All right. So then the last thing that we said from a process standpoint is we're going to look at the mixing point. So at the mixing point, we have M1 coming in, we have 30 kilograms per hour coming in, and we have M2 leaving. So we can find M2 at the mixing point is equal to 90 because we have M1 from solving it on the unit process number 1. So we can do the same thing. We can balance A and we can find the fraction in A in that second stream as well. So I went through kind of through this very quickly, but basically convince yourself before you leave this video, convince yourself that these are the streams that are actually at the mixing point, same with unit 1. And then you could use unit 2 to be like a back substitution potentially on your homework, something like that. Or you could use unit 2 potentially to find other things as well. So the idea is that the boundaries are really important. So let me pull up my boundaries again. There they are. Your boundaries are really important. They're going to be really important in terms of telling you what goes in and out of each thing. If you make a strategy like we did, it's going to make your life a lot easier on exams, and you're going to spend less time trying to just write random balances. So my recommendation is to do some kind of planning of attack in order to solve these 2 unit processes. And that's going to be it for example 4.5.